Obviously, everything has a pattern, as we said, because of the dynamics, and we obviously must look at the sea level rise patterns as well. And the global mean sea level rise looked at several places and then synthesized into a global mean picture. Obviously shows sea level rise is increasing, corresponding with the warming. So there is an actual warming and expansion of water, which is called thermospheric sea level rise, and then there are isostatic adjustments, post-glacial rebounds. In other words, remember that the continents were pushed down by the glacier and were pushed up in front of the glaciers. Glacier melting, those continents are going up. The continents that were pushed up are going down, and so on. So those are eustatic or isostatic adjustments and can cause local sea level rise. And then you have the other contribution, which is the melting of glaciers and ice caps, which is eustatic because it's distributed around the world. Okay, so here looking at some tide gauges, and you can see the anomalous rise in sea level since 1850 is about more than 40 centimeters on the west coast here off of California. A shorter record, but has a similar, let's say about 30 centimeters or so, and in the middle of the ocean, again about 10 20 centimeters or so. So melting of the Arctic, Antarctic and Greenland ice sheets is contributing to this. Remember that sea ice melting in the Arctic is not going to contribute to the sea level rise, because that's water that's already in the ocean. It's like an ice cube in your glass of Coca-Cola. Melting of that ice cube is not going to increase the amount of Coca-Cola, but the glacier that's sitting on land has been taken and frozen the water from the ocean, and when it melts, that's going to put it back into the ocean. So thermal expansion of the surface waters, deep waters, and glacier contributions and continental movements together determine the sea level rise, and then dynamics distributes the patterns of sea level rise. So here is the global average since 1880 with respect to the long-term average. So we are in inches now, so it's more than 10 inches. There's been satellite data. Remember the altimeters that we talked about that were measuring wave heights and so on. It's the same satellite that is launched for measuring sea level rise, and you can see that that is somewhat different than estimates from tide gauges and so on. So these bands you see around the dark blue line are kind of uncertainties or confidence limits. Because you have tide gauges only on land, you have to average them and make sure that you are carrying some measure of the uncertainty in your estimate. This is very critical, of course. But what's more interesting is here to reconfirm our contributions. So deep ocean thermal expansion is shown here in the yellow line. Melting of glaciers and small ice caps is shown here in the blue line. And melting of Antarctic and Greenland glaciers. The thing to worry about here is that they are accelerating. Like these are remaining fairly steady rises, whereas this one is accelerating. So just last week, 2 papers came out talking about Greenland shedding more, as I showed already, and another one arguing that some of the Antarctic ice sheets are reaching tipping points. They are called points of no return. Okay, remember glaciers take a long time to build, but the warming phase can go very fast, the ice albedo feedback. So that's what determines the surface thermal expansion and the global mean sea level. So projections are anywhere between 1.6 and 4.6 feet global mean. But as we said, Nobody lives in the global mean temperature or global mean sea level. I mentioned accelerated sea level increase in a few places. The east coast of the US is one of them. Here off of Asia in the Kuroshio extension region. And you can see the high stormy region of the Southern Ocean is obviously going to look like a stormy region. Okay, so ocean heat content from the surface to, let's say, 700 meters where the data is good, or down to 2000 meters where data is sparse, and so on, correspond to the sea level because of the thermal expansion being related to the heat content increase. Okay, so again, you can see the pattern here. Why is this important? Because you can see here there is maybe a negative heat content increase, negative here. And let's focus on this region again. Why is this important again? Let's say this is like the El Nino region, but this is also where ocean is bringing up heat by upwelling. Atmosphere is heating it, and then the waters are moving west, and the heat is being stored in the ocean. Some of it is being released every few years as El Nino. As we said, when El Nino happens, ocean releases the heat that it has accumulated, and then there is a mini global warming. But there is also a circulation which is moving this heat away and penetrating deeper into the ocean, right? So what is important? Remember that there is a positive feedback. You have cold temperatures here, warm temperatures here, high pressure, low pressure, winds, and positive feedback. So if perturbation increases the upwelling, temperatures get colder, pressure gets higher, pressure gradient and sea surface temperature gradient from the east to west gets stronger, winds get stronger, upwelling gets stronger again, so you have a positive feedback. Which means this is the ocean heat sponge. As long as there is upwelling, the ocean is soaking up the heat from the atmosphere. So we have to critically watch whether this region warms faster than this region or slower than this region. Why? Because if this region warms faster, then the gradient is going to get weaker. Winds will get further weaker, upwelling get weaker, more warming, less heat uptake by the ocean. So this is not an El Nino. Now we are talking about from decade to decade. Okay, the warming is happening on decade by decade, as we saw, right? There are year-to-year variabilities, but we are worried about how one decade is changing with respect to the previous decade and so on. Okay, so this region is very critical because if this warms slower than this region, that means the gradient can get stronger, winds can get stronger, more upwelling, more heat uptake by the ocean. So the atmospheric warming, the rate of global warming in the atmosphere, is controlled by this ocean's ability to take up heat and keep it away for a long time. El Nino does a little bit of release, but there is a heat uptake, as we saw, all the way down to the bottom, right? In the Southern Ocean, in the subtropical gyres, and in this region. So that's something you have to remember, that the warming in the East Pacific with respect to the West Pacific is going to be a big deal for how much heat will continue to go into the ocean and how that will modulate global warming, because literally global warming is modulated by the ocean's ability to take more than 90% of the excess energy and put it away for a long time. That's the more important thing. Ocean can put it away for hundreds, and if we are lucky, for thousands of years.